So we just introduced electronegativity, and now we're going to use electronegativity to predict what happens in bonds. All right, so we just said that electronegativity is the property of an atom to pull bonding electrons to itself. And we have seen that covalent bonds occur when atoms share electrons, and we're going to now determine how evenly these electrons are shared. So from the electronegativity table, which I've got a picture of, we're going to use the electronegativity of atoms at either end of the bond to determine how well the atoms in the bond share the electrons. So in the case here, we have a chlorine molecule. So chlorine exists in the atmosphere as Cl2. The chlorine atoms each have 1 valence electron, or 7 valence electrons. They have one place to form a bond. So when they come together, they form a bond by sharing 2 electrons. So Cl2 is how we find chlorine in the atmosphere, and a molecule looks like this. Okay, where the chlorine atoms have 1 bond between them, so they're sharing 2 electrons. If we look at the electronegativities of chlorine, the electronegativity of chlorine is equal to 3.0. Okay, so what the electronegativity is telling us is how strongly the electrons are being pulled by each atom towards that atom. And a 3.0 electronegativity is pretty high. It's the 3rd highest in the periodic table. But since these are both chlorine atoms, they're both kind of pulling with the same amount of strength at these electrons. So it's like 2 twins pulling a toy towards themselves, and they're at equal strength. And while they both pull really hard, the toy just kind of stays in the middle. And that's kind of what's going on here. So if my electronegativities are equal, then the electrons are exactly shared equally, and neither of the atoms gets to have those electrons around it more than the other. When that happens, we see that the electron density, so this is an electron density map, and what it does is depict how evenly the electrons are distributed around that molecule. And we can see here that it's all green, so it's all equally distributed. If we saw red or blue, red means electrons, there's a high electron density on that atom, and blue means there's a low electron density on that atom, and green means everything's equal. So this electron density map shows that the chlorine atoms are sharing the electrons in the bond equally. Now if we move something more to like HF, and we look at the electronegativities for H and F, we see hydrogen is 2.1 and fluorine is 4.0. So we have hydrogen that has an electronegativity of 2.1 and fluorine's electronegativity is 4.0. The difference between the two is pretty big, actually, which means that those electrons in the bond are getting pulled towards the fluorine and spend more time around the fluorine than they do the hydrogen. Okay, what happens, what that causes is it causes the fluorine to be slightly negative. It's not a full negative, it's not an ion, it's not like F minus, but it's that electron from hydrogen is spending some time around fluorine more than it is hydrogen. So it makes fluorine be slightly negative, and then it makes, so, and as a result, it makes hydrogen slightly positive. And what that causes is this thing called a dipole. And a dipole is simply a separation of charges. So in this case, one end, the fluorine end, is slightly negative. The hydrogen is slightly positive. So the charges are slightly separated, causing poles, a negative pole and a positive pole. So if we think of poles, you think of magnets that have opposite poles. This is the same kind of thing. There's a positive end and a negative end. So this is an electron density map. So when we saw the chlorine, it was all green. In this case, it's not all green. We've got a kind of blue or purple end down by the hydrogen. That means there's a lack of electrons over there. And the fluorine has a red end, which means there's an excess of electrons over there. So what happens is we get those electrons that were shared just aren't shared equally. They spend more time near the fluorine than they do the hydrogen, and it causes this effect. What that means is the bond is called polar. Okay? And polar means there's simply a negative end and a positive end. And to show this polar bond, we're going to do one of two things. We're going to use these delta negative or delta positive, like we've got here. And delta means partial. Okay, that curly D shape is a Greek letter. And it means partial. And it means fluorine's got a partial negative charge and hydrogen's got a partial positive charge. So it's not like this where fluorine has a full negative charge, or like this where hydrogen has a full positive charge. It's not that. It's only a portion of that overall charge. So it's not these. Okay? It's just partial. A lot of times we prefer to draw an arrow, and that arrow simply shows the direction in which the feel the strongest pull, and then we put a little cross on the end that is the more positive side. Okay, so that's called a dipole arrow because the molecule has a dipole. It's got a separation of charges. So a bond in which the electrons aren't shared equally is called a polar bond or a polar covalent bond. Since it's a covalent bond and the electrons aren't shared equally, it's called polar covalent, but typically we shorten that to polar bond. And if we're back looking at the chlorines, where the electrons are shared equally, that would be a non-polar bond, or a pure covalent bond, or a non-polar covalent bond. Typically, we just say non-polar bonds, or a pure bond. So then the question is, where do we cut things off? When is the bond not polar? When is it polar? Right? So how much electronegativity difference do we need before we say, yeah, that's enough difference to make it polar? There's no real clear cutoff. Every book has got a little different version, but this book basically says that if the electronegativity difference between the atoms that are bonded is between 0 and 0.5, then it's nonpolar. That the difference isn't big enough to make it polar. If that difference is between 0.5 and 2.0, then it's polar. The difference is big enough that the electrons are still sharing electrons, but one end is positive and one end is negative because the electrons spend more time around one atom. And then if it's greater than 2, we basically say that the atom with higher electronegativity has now pulled the electron away and made ions. All right? So right now we're going to kind of focus on the nonpolar and polar area. So basically, if it goes from 0 up to 0.5, but not including 0.5, that's how I do it. It's not polar. If it's 0.5 or greater up to 2, then it's polar. And if it's 2 or greater, then it's ionic. So let's practice. So let's determine if the bond that forms between these atoms is pure or pure covalent, meaning nonpolar covalent, polar, so polar covalent, or ionic. And that's going to be simply the difference between the electronegativities. So if we look up the electronegativities for carbon, which is 2.5, 2.5, and hydrogen, which is 2.1, we see the difference. 2.5 minus 2.1 is 0.4, and that's less than 0.5, so we would call the carbon-hydrogen bond nonpolar. All right? What about sulfur and oxygen? So if we look up sulfur, it's 2.5. And if we look up oxygen, it's 3.5. We always subtract the smaller one from the larger one. So 3.5 minus 2.5 equals 1.0. That means that falls in the range of a polar bond, that the electrons aren't shared equally, and actually they spend more time closer to the oxygen. So if I'm going to draw that, I'm going to draw an S and an O, and it says show the direction of the arrow. So remember, the arrow goes in the direction the electrons are pulled more, and then we put a positive sign, we cross the arrow on the end that's more positive. So when we have a polar bond, it tells us we need to show that. So the bond between S and O, sulfur and oxygen, would be a polar bond. Calcium and oxygen. Oxygen we just thought was 3.5. Calcium's electronegativity is 1.0. So 3.5 minus 1.0 is 2.5. And this is big. That's a big difference in electronegativity, and that's bigger than, that's greater than 2. So we would expect this to be an ionic bond, meaning that we would have calcium ions and oxide ions, and they would form ionic bonds. Okay. Nitrogen and chlorine. Nitrogen has an electronegativity of 3.0. Chlorine has an electronegativity of 3.0. The difference is 0.0. I can do that in my head. So we'd expect the nitrogen-chlorine bond to be not polar, that it would share those electrons equally. And then the last one is oxygen and hydrogen. Oxygen is 3.5, hydrogen is 2.1. So 3.5 minus 2.1 is 1.4, which is that's pretty strong. That's a pretty good electronegativity difference. It still falls between the 0.5 and 2, so it's still polar. It's not ionic. So the oxygen and hydrogen don't share the electrons equally. And since oxygen is more electronegative, the electrons are going to get pulled towards the oxygen more. And we'll put a plus sign down by the hydrogen because that's going to be the positive end. Okay? So now we can predict if a bond, how well atoms are going to share electrons when they form bonds. We'll do this primarily just for the covalent type of bond, where we have nonmetals or metalloids bonding. So we'll determine if the bonding electrons are shared equally, and if they're not, we'll label that as a polar bond, and if they're shared equally or close to equally, we call that a non-polar bond.